All right, welcome for section 7.2 notes. Today we're still going to be working on solving systems of equations, but we are going to be covering the other method, the elimination method. Elimination method is something that you guys are way more familiar with. It's probably the one that you guys wanted to do yesterday. It's the thing that you're sort of used to from Algebra 1. So we're going to go through it, and something to just be aware of is this is what we're going to use in section 7.2, but it's also what we're going to use in section 7.3. And in 7.3, we just deal with systems of equations that have multiple variables, so more than two variables. We're going to throw z in there and see how people panic. So the elimination method, when we're talking about that, this method, let's switch to a good pen for this, not that one. This method, the elimination method, combines the two equations by adding or subtracting equivalent quantities. So let's switch that minor spelling. This method combines two equations by addition or subtraction. And that's in order to create a new equation. That sort of goes off the page there. That's okay. Now, important thing about this, you guys are sort of used to seeing it as solely addition. When we talk about elimination method, that's the one where what you're looking for is to get exact opposites. So you want like +4 and -4 so that those can cancel. Not that it necessarily changes much, but keep in mind that if you were to get +4 and +4, you can just subtract straight down. I think I do it in one of the examples that comes up. So the goal here, much like the word elimination would tell us, is to eliminate one variable and leave an equation with one variable, so that that equation is then solvable, one equation with one variable. So we have 5 examples that we're going to go through. Some of them have a little bit of fractions, which is fun. So looking at this first example, solve the system of equations by elimination and verify graphically. Just like yesterday, we're not going to worry about the verifying graphically. We'll do that in class, but we will go through all the algebra. So I can eliminate either variable in this case. I can get rid of x or I can get rid of y. It doesn't make a difference in terms of your answer, but it does make a difference in terms of your work. You want to avoid doing more work. So it's a strong thing to recognize here that the x's are already exact opposites, +3 and -3, which allows me to add straight down. When I add that, the 3 x's will cancel, and I'll have 3y is equal to 6. Solving that, I get y is equal to 2. And now, just like the final step that we had in the substitution method, we substitute that back into either equation. I'll pick that top equation for no reason other than it's on the top, so why not? We'll have 3x plus 5 times 2 is equal to 7. We get 3x plus 10 is equal to 7. So 3x equals -3 and x equals -1. Your last step in all of these questions is going to be actually to give sort of a final answer, and that final answer in this case is a coordinate, x comma y, so -1 comma 2. Graphically, we have 2 lines. They should be intersecting in one point, and that point should be -1 comma 2. All right. Next, similar type of question. We've got 2 equations. They're both linear equations. But looking at the x and the y, neither one of them is necessarily easy to right away cancel off. You can get rid of either one in this case. It's going to be the same amount of work. In the case of what I'm going to do, I'm going to get rid of the y's. So on this top equation, I'm going to have to multiply the entire equations by something. You should be able to come up with what is the smallest number that both of these numbers, go into. So you're sort of looking for the least common multiple there. If you're not able to do that, just keep in mind you can crisscross these numbers. So I'll put the 4 on top and the 3 on bottom. I don't need to worry about the positive and negative because one of them is already positive and one is already negative, meaning they were already opposites. So I'm going to distribute this out to all 3 terms. I'll have 20x plus 12y, that's a terrible 12, plus 12y is equal to 36. And then I'll have 6x minus 12y is equal to 42. As you can see now, my y's are exact opposites, which means that I can cancel those 2 things off and add straight down. So I'm going to be performing addition. What I get is 26x, these cancel, is equal to 78. That gives me x is equal to 3. Once I have one of those variables, I'm able to substitute that back into either of these equations. Once again, I'm just going to pick that top equation for no reason other than for fun. And I'm going to have 5 times 3 plus 3y is equal to 9. In some cases, there will be a smarter equation to pick. In this case, it's not a big difference, but the top equation has all positives. This bottom equation has that negative, and sometimes we're not so great with negatives. So we'll have 15 plus 3y is equal to 9. 3y is equal to negative 6. So y is equal to negative 2. Our final answer is to then write that coordinate, which is going to be 3, negative 2. Again, graphically, if I were to graph this using my graphing calculator, I'd see 2 linear functions, meaning straight lines that intersect in one point, and that point should be 3, negative 2. Next question, we have 2x minus 3y equals 3, and negative 4x plus 6y equals 6. So in this case, I can get rid of either variable. Both of them look like they're pretty much the same amount of work. So I'm going to look at the x's. If I want to get rid of x, I only have to multiply this top equation. And what I have to multiply it by is just 2. If I distribute that 2, I'll get 4x minus 6y is equal to 6. In some cases, it's a little bit helpful to sort of just cross that off just because you don't want to accidentally add it in when you're now coming up with the new equation. We're going to perform addition here. The negative 4 and positive 4 will cancel. The negative 6 and positive 6 will cancel. And the 6 plus 6 is going to give us 12. Over here, we need something as a placeholder there, so we have 0 is equal to 12. Well, now you're thinking, is 0 equal to 12? No, it isn't. So that means that there's no solution here. And what that's also telling us is that these must be parallel lines. Your answer here would be this no solution. Parallel lines is more of like what's happening, but it's not the actual solution. Your solution is the fact that there is no solution because 0 is not 12. All right, moving into a very similar example. We have 2x minus 3y equals 3 and negative 4x plus 6y equals negative 6. Not the exact same problem. Only thing that has changed is now I have negative 6. So I'll start this the same way. I'll multiply the top by 2. I get 4x minus 6y is equal to 6. I'll cross that off. I don't want to get confused with it. And if I now perform addition going straight down, these cancel, these cancel, these cancel. Oh, so I'm left with 0 is equal to 0. Well, that's great. You know, it's not like 0 equals 12 or 4 equals 3. I'm getting something that is a true statement. So what this is telling me is that I have infinitely many solutions. More specifically, we can say that your solutions are all of the coordinates of x, y, such that 2x minus 3y is equal to 3. And here we're saying that our solutions are specifically all the combinations of x and y that would work for this equation. I could have picked the second equation. Notice this is just the first one. And what this is really telling us about the graph of this is that these are the same line. They are different equations, for the exact same line. So they would sort of visually be overlapping. If we were to graph this, you wouldn't even notice that there are two separate lines here. All right, and then one last example. We got to end on a really strong note and throw in these wonderful fractions. So we have 2/5 x minus 3/2 y is equal to -8, and -6/5 x minus 11/2 y is equal to -16. Now I know we usually panic when we're seeing fractions, but we're just going to go through this mentality and think the exact same thing. We can eliminate either x or y. If we look at the x's, both of them are already over 5. If we look at the y's, both of them are already over 2. That's a good thing for me. I don't have to necessarily worry about those denominators yet as much. But if I look at the y's, I have 3 and 11. The least common multiple between those two is going to be 33, which means I'd have to multiply both equations. If I look at the x's, I have 2 and -6. The least common multiple between those is going to be 6. And that means I'm only going to have to multiply this top equation. If I have -6 here, I'm going to want +6 up here, so I'll multiply by 3. As I distribute that, remember that you are only distributing to the numerators of these, and then as well to the -8. So I will have 6/5 x minus 9/2 y is equal to -24. Now I'm going to perform addition between these two equations. I'll lightly cross that one off. When I add -6/5 x and 6/5 x, that cancels. -11/2 and -9/2, that's giving me -20/2, which is -10 y. And -16 plus -24 will give me -40. This gives me y is equal to 4, which is nice. It's not a fraction. And I can pick any of these 3 different equations to substitute back into. I scratched that one off a little bit, but I'll still substitute into it. I'll have 2/5 x minus 3/2, and instead of y, I'll put 4 equals -8. This 4 is like 4 over 1, and the 4 over 2 becomes 2. So this is just a -6. If you don't like the way that I showed that, you can also say I'm doing 3/2 times 4, which is 12/2, which is still 6. 2/5 x minus 6 equals -8. 2/5 x equals -2, and multiply by the reciprocal, 5/2. Those cancel, so I'm left with x. These cancel, and I'm left with -5. Final answer here is going to be a coordinate, -5, 4. All right, that's it for section 7.2. Tomorrow we move into section 7.3, and what we're going to be talking about there is systems when we have multiple systems, more than 2, and multiple variables.